start kahit CB lang. So when we're talking about cyclic voltammetry or CB, okay, so this is just, we could say, the reversible reaction version of your what we call LSB. So when we have LSB, we scan the potential in one direction. Now when we have what we call the CB, we're going to scan it in both direction. So in LSB, we can scan it either to the positive potential or to a more negative potential. But in the CB, what we do is we scan it in both direction. Okay. So that's what we call the difference between LSB and cyclic voltammetry. So the way that you put cyclic voltammetry is there's a periodic triangular waveform similar to this one. So as you could see here, okay, you're going to scan it from 0.80 going to -2, and then from -2 to what we call 0.80. And then you can repeat it again, okay? So you can have that triangular waveform, and then you do it there. So you just keep scanning them in what we call one direction, okay? So we can say that the time that we have here, let's say within 20 seconds, you have one scan going to more negative, and then the next 20 seconds, one scan going what we call positive, and then another 20 seconds going negative, another 20 seconds going to what we call positive. So this time that we have here, that's what we call the linear voltage ramp. And usually in CB, the order of time that we have there when we ramp up the potential is within seconds. Okay, so the way that we use CB is to, we could say, what? What is the use of CB? If you read the article that was given to you, or we could say the thesis that was given to you, usually it's used to characterize the redox properties of the compounds that you have in a given system. And in addition to that, you can also look at the mechanisms that you have. Okay, so usually what do we have here? So maybe in one direction you have this. So the reduction form being converted to an oxidized form, and then the oxidized form being converted to the reduction form. Now, the thing is, CB is what we call perform in an unstirred solution. Okay, so if you perform what we call CB, so usually this is really what you're doing. So you're going to get initial potential from here, more negative going to more positive. So this corresponds to where? This one. And then you're going to do it here. Now, if you repeat this again, like this one, you repeat this again, this one, what do you think happened here? You're going to have another voltammogram that is similar to the initial one. So if you're going to look at the what we call CB that is happening here, so this one triangle here that you have, that is, we could say, one cycle. So if you put a second cycle, you have another what we call voltammogram on this one. Okay, so a cyclic voltammetric experiment, it can be made up of what? One cycle or many cycles. Now you can start it from here, going there, or you can start it from here, doing the other way around, like this one. So what will happen? So if you do it like this, going here, so you can start that thing. Okay, you're going to reverse here, the what we call reaction. Now, as you could see here, okay, you have what we call a peak current. So IPC here, and you have what? IPA. So what that would mean? This is the current, okay, or a peak current cathodic reduction. And this is the peak current at the anodic reduction, or what we call anodic direction. Okay, and the peak current in CB, usually they are governed or given by the Randall's Sebsic equation. So usually it's just IP equals to 2.69 times 10 to the 5 n raised to 3/1/2 times AD raised to 1/2 times B raised to 1/2 C times A. So which one do you know here? What is N? Anyone?
Number of electrons po, sir.
Okay, N means number of electrons. Now, which one do you know here? A, what do you think is A?
Area po.
Area of the working electrode.
Yes, electron.
Okay. D is, ano yung D na associated sa topic natin sa voltammetry?
Diffusion.
That's diffusion coefficient. And this is for the electroactive species. And then B, what do you think is the B?
Scan
That's the
rate
scan
po.
rate. Okay. And A is equals to the concentration of the electroactive species. Now, if you're going to look at the paper that I asked you to write, they have different what we call modifier there. So the one that you have there is what we call modifier that contains electroactive species. Now, if we have a what we call well-behaved, or we could say symmetrical CB, okay, we could say that IPA is equals to IPC. Okay, if they are what we call symmetrical. So both the anodic and the cathodic peak currents, they are what we call equal. And the ratio of IPA over IPC is what? 1. Kasi equal sila. Okay? Now, the half-wave potential that we have here, that's E1/2, usually, oh no, where did I do? Okay? That is just equals to the potential at the, what we call anodic plus the potential at the cathodic over what we call 2. So that's midway between the anodic and the cathodic peak potential. Now, what makes it a good, we could say, tool for characterizing the redox potential of your electroactive species is it allows you to explore, okay, in both directions if you contain one or two or several what we call the active species. And this is, we could say, the main advantage of CB, the distinct advantage of cyclic voltammetry over other voltammetric analyzer. Okay, now if you're going to look at how it looks like, so this is what the cyclic voltammogram of hydroxyperoxine. So if you're going to look at this, it has a cathodic peak here, and it has an anodic peak. So we could say the reaction that you have here is reversible. Okay, the oxidation and reduction are, we could say, the same, or the electroactive species that is oxidized and reduced are what we call the same. Okay, so if you're going to look at the peak potential there, variations of the rates, okay, it can change the thing here. I have an example because today I just give you a different example of the CB. Okay, so if you look at the peak potential, you have the anodic peak current, the one here, and then the cathodic peak current that you have here on top. Okay, so there's always a difference of 0.0592 divided by the number of the electrons. So that's an inertial equation. Okay, so peak potentials and peak currents on the other, that's the line to peak. Anode is what we call slope to bottom. So usually the peak currents are equal, okay, but opposite sign. And the thing that you learn here is the mechanisms and the rate of the redox reaction. Okay, so it's really what we call useful. So this is another way of presenting here. So this is the peak potential that you have. Okay, so this is what, look at how they are what we call the deeper. Okay, because in some conventional, if you're going to look at this, wait, not that one. So how is this what we call different from the first one?
IPA po sa taas.
Okay, yung A yung nasa taas, tapos yung cathode yung nasa baba. Because if you tweak them like this one, okay, it's just the same. It's just that it started on this going to this one. Now the previous one that I have here, it started on this going to this one. Okay, so parang clinip mo lang siya. So usually the European and the American convention, they always what we call the opposite. So that's why you have to understand how it is. Okay. Now, if you're going to look at what is really happening during this, what we call cyclic voltammetry, or when you do the scan at both directions. So here, what do? I put the reduction on top and then the oxidation on the other one. So the way that we're going to sweep this, okay, or ramp the potential is from a more positive going to more negative. So starting at the positive voltage, so initially there's no current. And then what happened here, if there's a reducible species, okay, is present, the current for the cathode will increase, okay? And then you keep what we call scanning it to a more negative, it continue to increase the current until all the species is reduced, okay? So we could say the peak current there at the cathodic direction has already reached the minimum, and then it starts to decrease until it again reaches the background current level, okay? Now the potential is reversed, so you reach the opposite end, okay, of your sweep. So what happened as you ramp the voltage, okay, becoming more positive, the reduced species can be oxidized, okay? And what you have here, it goes to what we call the current of the anodic, okay? It reached the maximum. So when you say maximum, it's the lowest on this side here. And then this is where all of them has been oxidized. And then the current peak anodic decreases back to the background level. So if you're going to look at the important features of a cyclic voltammetry, Okay, you usually look at the what we call peak potential in terms of the cathodic peak potential and the anodic peak potential. So usually they are what? The same. Okay. So this is one way for you to look at it. Now, if you're going to look at it this way, so here it shows you, it's just the same as what I have initially shown, but it shows you at different point and how the cyclic voltammetry looks like. So initially at A, so you have here at A, okay, and then you sweep with time from the more positive going to a more negative. So B would go here, C, and then D is the one that is, we could say, at the maximum for the peak current at the cathodic direction, and then E, and then F. So F is the most negative potential that you have. And then you sweep it again to make it positive in terms of the potential. So it's just going to what we could do the reverse as you have said, this one. So in theory, if you have just the same electroactive species that can undergo redox reaction, this is the typical cyclic voltammograms that you're going to what we call observe. And if you're going to look at this, I put here, a CB is just a method used to look at the mechanisms of the redox reaction in solution. And when you have a CB, you look at the current versus the potential response of small stationary electrode in unstirred solution using the triangular waveform for what we call excitation. And if we're going to look at a specific example, so I have here potassium ferrocyanide with KNO3. So it will tell you, okay, what is happening here in the given system. So the initial negative current that you have there is due to oxidation of water to give oxygen. And then as you increase, okay, the potential, you make it more negative. Okay, so there's no current between A and B, point A and B. That's between 0.7 and 0.4 volts. Okay, that means there's no reducible or oxidizable species present in this potential rate. Okay, but at 0.4 B, at 0.4 voltage, current begins because of the following reaction. So as you could see this, okay, so this is what? Oxidation or reduction? Ano reaction to?
Reduction po, sir.
Okay, so this is what we call reduction. Okay, so here, there's all reduction that is happening. And because of that, you start to form the current. Okay, so the current increases as, okay, there are more of the material that is what we call reduced. So this is from B going to D. So D is the maximum peak current that you will be able to obtain. Now, once you get the cathodic peak potential and the peak current here, the highest point, it starts to decrease. Okay, the current decrease rapidly as the diffusion layer is extended farther from the electrode surface, and the scan direction would switch. Okay, so from the 0.15 volts negative, okay, it will now go to a more positive one. Okay, so the potential that you have there is still negative enough to cause the reduction of your material. And then what happened if you switch in the opposite direction? So reduction don't occur, and what happened now is oxidation is the one taking place. Okay, so this one will be reduced to give you the previous electroactive species. So that is, we could say, a good way to tell you that your material can undergo a redox reaction. Okay, so the lowest point that you have here, or the maximum, that you have between this and the background that you have there, that is the zero. Okay, that is your anodic peak potential and peak current. So this is, we could say, very useful. A very simple method that is very useful in characterizing, okay, the electroactive system that you have in your working electrode. So here you use what? A platinum as a working electrode, and the reference electrode is SCE. Now the one that you're looking at is a system, okay, K3 FeCN6 with in 1 molar KNO3 supporting electrolyte. Okay. Now, if we're going to look at the quantitative information that you can get there, so you can get what? The current peak in the cathodic direction and the current peak in the anodic direction. So you can get the difference in the peak potential. So this is just equals to what? The peak potential at the anodic direction minus the peak potential in the cathodic direction, which is just equals to 0.0592 divided by N. Okay. And this one that you have there, the potential that you have there, that's the midpoint of your potential, peak potential at the anodic going to the peak potential at the what is called cathodic. And you have here, okay, what we have discussed before, which is your Randles-Sebzig equation. Okay, and giving you electrode area, its concentration, scan rate, and diffusion coefficient. So the information that you can get here, if you have a CB, you can calculate for the standard potential for the half reaction, the number of electrons that involved in the half reaction, the diffusion coefficient, and if the reaction is reversible. So if you see a mirror image, if you can flip them and you could see the same thing, so most likely the reaction that you have there is reversible. Okay, so that's the usefulness. Now, I don't know if you see this in the paper that were given to you, because in some, you only have that, and then what do you have? It's just like this. So that means the opposite direction reaction didn't happen. Okay, so usually what happened there, if I'm not mistaken, is just what? The reduction reaction. Okay, I don't know. You can look at the CB of the paper that were given to you and see if it's like this one. So if this is like this one, like a duck, as we call it, then you have a reversible reaction. But if not, then there are other electroactive species that you have in a given system. Okay. Now, the information that you can get in the cyclic voltammetry, you can have some applications to it. I just put some here. You can determine the number of charge. The integrated area under each weight represents the charge associated with the reduction or oxidation of the absorbed layer. Okay, so the charge is just equals to the number of electrons, Faraday constant, times the area of the electron times the surface coverage in moles of the adsorbed molecules per surface area. Now you can also determine the capacitance, as the peak current is proportional to the scan rate. Okay, so this one is just the capacitance. Oh no, this is the I current, current, and then it's equals to the scan rate times the capacitance. Now, in addition to this, you can determine the number of electrons that is involved in the reversible reaction, the difference in the peak potentials. Okay, it's expected to be like this one, based on this given formula. You can also determine the surface coverage. When the number of electrons is known, the surface coverage can be calculated by this equation. So these are just some information if you're going to use CB in details. Before, you can make a paper by just running a CB of a certain compound. And I'm going to show you some of them. Okay. Now, the problem that they have is the so-called baseline issues. So what can you say about this? Can you say this is a reversible system? So this is just, we could say, platinum in 0.5 molar sulfuric acid at a scan rate of 40 millivolts per second. So the difference of this over this one, so this is what? Benzene in 0.5 molar sulfuric acid. So there is a difference that you could see here. So look at the difference in this one. So you have here two scans. The one in the dotted line is the second sweep. So you see the triangle that I put there. So this heavy line is the first triangle, and the second triangle is the what we call dotted lines. So why are they not the same? If I ask you to interpret the CB on this one, how are you going to interpret this? For the first one, can you say they're reversible? Anyone?
No po ata, sir.
Okay. So the only thing that you could say, maybe this is, we could say, the same species here, but the concentration that they have is what? Not the same. So maybe you have other species that undergo oxidation on this side. Okay. So we could say there are species that undergo reduction, and when you reverse the direction, some of that undergo reduction, also undergo oxidation. But in addition to that, there are other species that also undergo oxidation. Now remember, what could that be? So you have here sulfuric acid. So you can look at the redox reaction that involves sulfuric acid. If you're going to look at the reduction potential, you will see that there are different reactions of the sulfuric acid. Am I right?
Yes po.
Okay. So that could be the what we call explanation here. Now here, what happened? Why is it that when you do the second sweep, it's not the same as the first CB? Anyone? So this is the study that they have before when CB is new. So they just try to look at it. And based on the sweep, they can already determine the mechanism that is happening here. So we could say that on the second sweep, you don't have this anymore. You don't have this anymore. That's the only explanation that you have. Why? Because you don't see this peak here. What you have instead is another peak that is reduced at this potential. But there's no more peak, okay, when you oxidize the system. So maybe what might happen, so when it undergo reduction, it is converted to something, and it was not reduced anymore. So another step was reduced. So when you sweep it again, so the peak that comes at this potential is different from that one. So ganyan na yung pag-explain doon sa what we call CB. Or you can do it this way. So what do you think is consistent among this voltammogram? You always have this. The only one that is different is what? The metal, right? So you have there a CO4 And then you have here a chromium, a molybdenum, and a tungsten. Now, which one is almost the same?
Tungsten and molybdenum.
Ito yung almost the same. If you're going to look at this, they're almost the same. Now, what is the one that is being difference? Is this one. So why does this thing has this extra anodic peak compared to the other? So maybe it has something to do with the nature of the chromium that may undergo what? Reaction, okay, together with the other component that you have there. So see, they have almost the same system, and then you have what? Chromium is the only one that is different, and you could see the difference. And in addition to that, we could say this is a higher peak current compared to the other two. What is this, what we call difference between the three? If you're going to look at the periodic table, chromium, molybdenum, tungsten. Sige nga, tingnan natin yung periodic table. Trying to open a periodic table so I can see the difference of them. So here we have chromium, molybdenum, and wolfram. So what can you say? All of them in the same group. But why is it that chromium is different compared to the other one? Okay, so that's what we call, that information can be provided to you by cyclic voltammogram. Okay, so in addition to other applications that we have, as I have told you, it can study the reaction mechanism. So the ligand exchange reaction as in iron porphyrin complexes that can be utilized here. And the example that I gave, that maybe your metal there can act as a ligand. Okay. And then there's the oxidation of chlorpromazine to produce a radical cation and subsequent reaction with water to produce sulfoxide. You can also look at the oxidation of dopamine in the presence of the ascorbic acid. And you can apply electrochemical stuff. So for instance, and see what happened for compound like aniline. So you can oxidize it and see how the mechanism would look like. Quantitative determination can also be useful. So you look at the concentration of the analyte, like the number of the electrons per molecule in the analyte. So maybe you look at this, what we call diffusion coefficient. Now, you can also look at the reversibility of the reaction. Okay, so to evaluate the electrochemical reversibility by looking at the difference between the peak potential for the anodic and the cathodic scans. So if they are reversible, usually, okay, you're going to have, like, if you have a peak here, most likely have a peak there. Now, if you don't see that, so maybe what can happen? There could be some intermediate that's formed. Maybe this one. Okay, so there's something here that can only be found if you have chromium, but not molybdenum and tungsten. Okay, so for example, for a 2-electron reduction, we expect the difference in the potential of approximately 29.6 millivolts. So for an electrochemical irreversible reaction, the value of change in the peak potential will be larger than expected. So that's a way to differentiate them. Okay. Now you can also use it in adsorption study in CV. So this is the repetitive voltammograms for riboflavin at hanging mercury drop electrode. So note the peak separation is smaller than for solution phase couple. So peak area also gives coverage. So using this formula or equation, okay, you'll be able to determine the area occupied the molecule and can give us the orientation information. Ferrocene was irreversibly absorbed in the form of SAM to a gold surface using long chain alkyl cation. So you see the potential of this method. Okay. And then you can use it for corrosion studies. So you can do some cyclic studies here. So these are different sweeps. So this is, we could just say, several triangles that you applied. Okay. So this is a potassium ferrocyanide in 0.1 molar KCl solution. So the red, that's a 20 millivolts scan rate. The gold that you have there, 50 millivolts scan rate. The green that you have there is what, 100 millivolts scan rate. So you just change the scan rate there and see the difference that you have. So they use it in corrosion studies. So corrosion is what? A redox reaction. So they look at the mechanism of corrosion. So it proceeds at about the same rate all over metal surfaces, uniform, and corrosion at discrete sites on the surface, okay, pitting crevice and stress corrosion cracking localized. So determine the degree of localized corrosion, the amount of Heiter S's between the positive going sweep and the negative going sweep is calculated. So this has really, we could say, a large potential. Because if you're going to look at the fundamental or primary use of the CB, it's a tool for fundamental and diagnostic studies that provide qualitative information about the electrochemical process under various conditions. You can look at it, let's say the application or the behavior of pesticides, if you apply it in agriculture. Okay, and I think I have that. So if you have a reversible reaction, this is how it looks like. So this is a 5 millimolar ferrocyanide in 50 millimolar KNO3. Scan rate of 100 millivolts per second. Now, if it's quasi-reversible, so as you could see here, you have both the cathodic and anodic peak, but they are not proportional as the one that you have here. Okay, so as the reaction approaches irreversibility, the peak separation becomes greater. So this is a hydroquinone in pH 7 phosphate buffer at a scan rate of 500 millivolts per second. Okay. So what can you say about this one? What if I tell you that this has the same compound? Are you going to believe me? What's the only difference between the two? Scan rate. But they have the same compound. So this one has a scan rate of what we call faster one, and this one has what? A slower one. So what can you say? What is the one that is being studied here? Is still mechanism? How are you going to interpret this one? You have the same system, but one has a faster scan rate compared to the other one. So paano mo interpret yan? Anyone who wants to try? Anyone? Hello? I think this is one of the advantage of CB compared to the other analytical method. So they provide you qualitative information. So they are the same redox couple reaction, one at a faster and one at a slower, what we call scan rate. So what's the possible interpretation here? At faster, we see what? 1, 2 peaks. Okay. At a slower, we only see 1 peak. So what does it mean? At the slower, you don't see the reduction peak. So one interpretation here, at the faster rate, okay, whatever product you have there were able to participate in the redox reaction. But at a much slower rate, okay, we could say the product that you have is not electroactive. Okay, because you don't see the peak at the what we call reduction. So one explanation on the difference of the two, the products from the reduction of R have sufficient time to participate in the chemical reaction here. But on this one, at a much slower rate, we could say the product of R is not electroactive to undergo reduction. Okay, so you just change the scan rate and you can see, you can get information out of it. Now, other example that I have here, so this is acetaminophen. So you're familiar with acetaminophen, right? That's what I drink because I have a headache after the trip in New Jersey. No, it's also the weather. The weather drops to 40 Fahrenheit this week. So this is a Tylenol. So if you're going to look at this, so this is the reaction that is happening there. So as you could see, this is what? The cathodic peak, and this is the anodic peak. It's different. Okay. And as you could see, when it undergo redox reaction, the structure that they have is really what we call different. And this is reflected in the cyclic voltammogram. So as a mono-substituted aminophenol, it is electrochemically active. Now the voltammetric behavior indicates a 2-electron oxidation at moderate potential with significant but not total ideal reversibility. That's why the CV that you have is different. Now, how about this one? Caffeic acid. So what can you say about the caffeic acid? Because say they are what? Reversible. Because you have the reduction peak here, and then you have the oxidation peak on the other hand. So they're almost what we call the same. And then this one, desipramine. So this is an antidepressant. Okay. And as you could see here, when it undergo oxidation, it formed a product that is different from the previous one. That's why very small here. Okay, this one we could say the same, but that means you have an intermediate that produce this peak. So usually it's a product of oxidation because it is produced on the anodic current peak. And then we have this one. So naproxen. Are you familiar with naproxen?
NSAID po, sir.
Yep. Do you have this brander? Alib?
Wala po ata sa Philippines.
Wala. Okay, so naproxen is an NSAID, non-steroidal anti-inflammatory drugs. Okay, so as you could see here, when it undergo oxidation, something is formed that can only be found on oxidation. So the explanation that they have their extended conjugation and may be enhanced by the ring alkyl substitution as well. So see, you get information, qualitative information if you use CV. And then you have here uric acid at carbon electrode. Okay, and again, saan mo siya makikita? Doon sa anodic current. So this is a classic example of a chemically irreversible process. And then this one. So this is a parathion, an insecticide that is used in agriculture. So they use a hanging mercury drop electron at this scan rate. So see what happens here. So you may ask yourself, how do we interpret this, what we call thing here? There are how many peaks you observe? Anyone?
3 peaks po.
So you have one here, another one here, and another one here. Okay. So the question, how are you going to interpret them? So the first peak, what is that? It's a reduction, right? A product of the reduction. So maybe this is the what we call formula that you have for this parathion. And then you have 4 electrons there reacting with H plus to produce. Okay. The way that you have here, this becomes what? NHOH plus water. So from your NO2, you have what? NHOH. So it was reduced. One of your oxygen was absorbed by water. Now, how about this one?
Oxidation, sir.
So this is oxidation. So whatever you form here, okay, it's going to produce now NO. So you lose one of the hydrogen there. Okay. So in addition to that, you produce H plus and 2 electrons. So this is the oxidation of the hydroxylamine to a nitroso derivative during the reverse scan. So from the nitro that you have here, it becomes what we call the hydroxylamine. Okay. And then from the hydroxylamine, it becomes nitroso. So this is, we could say, the B. This is the A, this is the B. And then you have another product that is formed here.
Reduction.
So this is what? Reduction. So your nitroso becomes what? Hydroxylamine again. So from your NO, it becomes NHOH. So we could say this is the one that sorts of the reversible. But this can only happen if you produce first, okay, your parathion into an hydroxylamine. So ito yung parang mirror image ng dalawa compared to this one. So this is produced when this is reduced. And then I have another one here. So this is what? Tyrosine. So what is the difference that you have here? So this one, you have platinum electrode. And this one, you have a graphite electrode. So this one is just for the ferrocene. So I would say they are reversible in both of them. So you can use the CB for the modified electron, like this one, the graphite electrode with attached pyridine, ruthenium, amine. So this is, we could say, one way of determining the electrochemical property of a system that you have, which in this case is the so-called modified working electrode. Now, with the advent of computation, okay, they use the so-called digital simulation for the chemical phenomenon, and it's a potent tool in fundamental investigation. So through the years, they developed software that try to simulate, okay, the electrochemical property of some of the compound. And the example that I have here is this one. So you have here the blue one as the experimental. So they try to simulate the cyclic voltammogram of your ferrocyanide at 1 molar KCl using the diamond electrode, and then using what we call the simulation. And as you could see, there's a great agreement between the simulated cyclic voltammogram with that of the experimental voltammogram. There's just a little bit, we could say, way off, offset, but okay, this is the best, we could say, simulation that you can get. Okay, and they say that it is offset because the simulation only represents the so-called what? The Faraday currents, while the one that is the experimental, it represents both the Faraday and non-Faraday current. Contributions of the Faraday and non-Faraday current. So that's, we could say, the power of cyclic voltammetry. So that I will end the session that we have today here. And I will ask you to have a break already because I don't think I can make the quiz. So I was supposed to post it last night, but I just have a headache after we arrived from New Jersey last weekend. So break na kayo. as posted by Carmel. Bakit pa mag-aantay sa 28 kung pwede namang mag-break bukas? Question? Anyone?